Now we want to introduce, to remind you, to review what's the definition of a null space. Okay, the null space is a matrix, is the set null A of all solutions of the homogeneous equation AX equal to 0. Okay, so it's all the solution set X such that AX equal to 0. All right, so we have a theorem here. So a null space of an n by m matrix is a subspace of Rn. Equivalently, the set of all solutions of Ax, of the system Ax equal to 0 of m homogeneous equations. This probably should be, sorry. This probably should be m by n. So let's see, can we change that or not? Cannot change that, let's see. 12. All right, so should be m, let's see, times n. Okay, n by n matrix is a subspace Rn. Equivalently, the set of all solutions of a system Ax equal to 0 of m homogeneous linear equations in n unknown is a subspace of Rn. So how do we prove that? This is a subspace of Rn. Okay, so the null space of a matrix. So we want to say null space of A is a subspace of Rn. How do we do that? Remember, the three things we need to show there, right? First is 0 vector in null space of A. Obviously, Ax equal to 0, x equal to 0 is a solutions. So x belong to, no, sorry, not x, 0 vector is an element of the null space. Second, we want to show that any two elements from the null space A added together still belong to the null space. So remember what's null space? Null space is a solution for Ax equal to 0. So let U, V belong to the null space of A. So what does that mean? That means AU equal to 0 vector and AV equal to 0 vector. So what about U plus V? Let's apply that. Let's apply A to U plus V. Well, by matrix additions operations, this is equal to AU plus AV. Well, by the choice of U and V, which is from the null space, we know these two guys are 0 vectors, therefore the sum is 0 vector. So we realize when you apply A to U plus V, it also equal to 0. So this implies U plus V is in the null space of A. Finally, we want to know if you multiply an element from null space by a scalar C, is it still in the null space or not? So let U belong to the null space of A. By definition, this means A U equal to 0. So consider C times U. So A applied to C times U. Okay, is C times U in null space or not? Well, by matrix operation, this is equal to C times AU. And, well, since AU equal to 0, this is C times 0. Therefore, this is a 0 vector. So CAU also belongs to a null space of A. So the null space of A qualifies for all three requirements of being a subspace. Number one, 0 is in there. Number two, the sum of element in the space in the set is still an element in the set. Finally, multiplied by a scalar from the of element from the set is still an element of the set. Therefore, it qualifies for that.